For 40 years, engineers refused to build it, not because the technology didn't exist, but because the problem had no solution anyone was willing to sign their name to. A bridge across a valley 270 meters deep, in a wind corridor that routinely destroyed equipment, on a limestone plateau with no viable anchor points for conventional foundations. The French government wanted a continuous highway. The Valley of the Tarn, carved over millions of years into the massive central, simply said no. France's A75 motorway had a gap in it, a 2.4-kilometer gap hanging above one of the deepest gorges in Europe. The massive central plateau sat on one side. The medieval town of Millau lay below it, and 270 meters of open air stood between them. A chasm that made every proposed design either structurally impossible, financially absurd, or both. Every solution engineers put forward ran into the same wall. The columns would have to be taller than the Eiffel Tower. No one had ever built a road bridge that high. No one was sure the physics would allow it, and nobody wanted to be the engineer who spent €1 billion proving they didn't. For decades, the project sat in a drawer. Then Michel Viaduct looked at the problem differently. He didn't ask, "How do we build columns that tall?" He asked, "How do we stop the columns from carrying all the weight?" The answer was cable stays, steel cables running from masts at the top of each pier directly to the deck, distributing the load the way a suspension bridge does, but anchored at every column instead of 2 end towers. It sounds simple. It wasn't. The Millau Viaduct required 7 piers. The tallest, Pier 2, rises 245 meters from the valley floor. Add the mast above it, and the full structure reaches 343 meters, 19 meters taller than the Eiffel Tower. But height was only one problem. The Tarn Gorge is a natural wind tunnel. Gusts routinely exceed 200 kilometers per hour. A flat deck at that altitude behaves like a sail, catching the wind, vibrating at resonant frequency, and eventually tearing itself apart. Engineers had watched this happen at other bridges. The Tacoma Narrows in 1940, the collapse was filmed. Nobody forgot. The team tested over 100 different deck cross-sections in wind tunnels before landing on a blade-shaped profile, a geometry that slices through wind instead of resisting it. The deck also curves, both horizontally and vertically, following the contours of the landscape to reduce aerodynamic loading across its full length. Nothing about its appearance is decorative. Every line is a calculation with a consequence. Building it required inventing construction methods that didn't yet exist. The valley floor was inaccessible to heavy equipment, so engineers constructed the piers from above, using hydraulic climbing formwork, a self-rising mold system that ascends automatically as each layer of concrete is poured and sets. Each pier grew at a rate of roughly 4 meters per day. Then came the deck. The roadway was fabricated in sections on both sides of the gorge, then pushed outward, millimeter by millimeter, from one elm over the tops of the completed piers using hydraulic jacks and temporary steel legs. At its maximum extension, the deck cantilevered 171 meters beyond its last support. Suspended over open air, nothing beneath it but valley and the town of Millau, 270 meters below. GPS guided every movement in real time. Tolerances were measured in millimeters. One miscalculation at that height meant dismantling an entire section from a structure with no ground access. It moved without a single error. The Millau Viaduct opened on December 14, 2004. Construction took 3 years, faster than nearly anyone had predicted when the first shovel broke ground. The final numbers: 290,000 tons of concrete, 19,000 tons of steel cable, 2,460 meters of total span, 500 workers on site at peak activity. Total cost: approximately €394 million. For a structure of this complexity, by any historical measure, so it can considered modest. Crossing it today takes 4 minutes. Before it opened, the only route dropped 520 meters into the valley, passed through Milau's narrow medieval streets in summer traffic, and climbed back up the other side. In August, that detour could swallow 3 hours. Now drivers pass above the clouds. There is a moment, just past the first pier, where you look sideways and see nothing but open sky and the valley floor far below. The town of Millau looks like a sketch. The horizon reaches further than it should, and for a few seconds the concrete beneath your wheels feels less like infrastructure and more like a refusal, a decision someone made to not accept the problem as it had been handed to them. Michel Virloge did not build the highest road bridge on Earth by being smarter than every engineer who came before him. He built it by refusing to solve the same problem they had been trying to solve. For 40 years, the question was, how tall can we build? He changed the question to, what if height is not the constraint? And that shift, more than 290,000 tons of concrete, or 19,000 tons of cable steel, is what the Millau Viaduct is actually made of. The most impossible structures are not overcome by force. They are overcome by someone who looked at the problem and decided the problem itself was wrong.